Hi guys, welcome to this set of videos. These videos are going to follow along with the notes that come out of your textbook from Chapter 8, Section 3. And as you can see from the title behind me, now just like every other chapter we've done in Algebra 2, we get to the graphing part. Now hopefully what you've kind of had this sense of as we move through Algebra 2 with all of the graphing we've done, that we've kind of been building to something, right? We started the year in Algebra 2 by looking at graphing linear functions and then graphing systems of equations. From there, we moved on to graphing quadratics and graphing polynomials. From there, we moved on to graphing radicals, exponential functions, logarithmic functions, and now here in Chapter 8, we really kind of come to the climax of the graphing we've been doing in Algebra 2 with graphing rational expressions, or rational functions rather. Now, all of the stuff we've been doing all through Algebra 2, from transformations, where we look at the value of a, h, and k, and how those guys kind of move the functions around a coordinate plane or change the shape of it. We'll still do all of that here for rational expressions. But rational expressions have a number of interesting characteristics that we're going to show you how they kind of come out in the algebra that we can do with these rational expressions. Rational functions have vertical asymptotes and horizontal asymptotes, and we really haven't seen those that often. Rational expressions can have slanted asymptotes, and we've never seen that. Rational expressions can also at some points have holes in the graph, which we call the indeterminate form, and we've never come across that before in Algebra 2. So lots of really interesting characteristics. As we go through some of these problems over the next couple of sections, you're really going to kind of get the feeling of what it's like to be a graphing calculator, and we'll show you how the algebra helps you pick out all of these interesting characteristics that rational expressions have in their graphs. Before we jump into that though, let's get some objectives or learning targets to kind of help us focus as we make our way through this set of notes. Guys, here's the things you'll need to be able to do when it comes to graphing rational functions. First, you'll need to be able to determine the limitations of the domain and range of the graphs of these rational functions. So first, again, just like in the previous sections, when it comes to rational functions, all right, can't divide by zero. Division by zero is not allowed. So we're going to need to be able to restrict both the domain and in some cases the range. And we'll show you how that works. And then we'll take a look at actually graphing some very simple rational functions to kind of get us started. And then in the next couple of sections, we'll get to more and more complicated ones. So here we go. First, the rational function. We're going to start with the parent function and the, sorry, that's my pen. I want my highlighter. There's my highlighter. The reciprocal function is essentially the parent function for rational functions, and it's just this guy right here, f of x equals 1 over x. This is the parent function for rational functions, all right? So this is with no transformations, all right? In this guy, let me make a couple quick notes for you here. This is the parent function. This is with no transformations. All right, so the parent function for all rational functions is this reciprocal function 1 over x. Please notice it is rational. I have a numerator, I have a denominator. And the simplest one is when you have 1 over x, where the variable is in the denominator. Now, for this parent function with no transformations, which means a is equal to 1, h is 0, and k is 0. What that means then, right, is the parent function is going to look like this guy, which is really kind of odd. We've not really seen anything like this before. It's known as a hyperbola. And again, really what it is it's a graph where, right, your values of, well, the way the graph looks is you're going sweeping down in the third quadrant, and then you've got this concave up, this concave up part up in the first quadrant, known as a hyperbola. Really what I want to point out to you is this right here. This parent function, all right, this parent function has a vertical asymptote at x equals 0, or the y-axis is a vertical asymptote, right? That's going to be a line that the graph will approach but never touch. And then also please notice the hyperbola has a horizontal asymptote at y equals 0, which is the x-axis. Again, it's a line the graph will approach but never touch, which is where you get this kind of odd shape for the reciprocal function. And it should make sense why there's a vertical asymptote at x equals 0. Please notice in the parent function, what happens if x is 0? Well, if I let x be 0, then I wind up with a 0 in the denominator. And we just spent 2 sections, Chapter 8, Section 1, Chapter 8, Section 2, talking about how division by 0 is not allowed. In fact, we did a ton of problems where we simplified rational expressions, and then I had you guys restrict the domain, right? Remember doing that? You restrict the domain, you tell me what values are not allowed in the denominator so that you don't get 0. Why did we do all of that? Because we were going to be graphing, right? You need to be able to restrict the domain. I cannot put a 0 down here. Division by 0 is undefined. Why is it undefined? Well, because I get a vertical asymptote. It is no coincidence that 0, right, if x is 0, gives me division by 0, and x equals 0 is a vertical asymptote. That is exactly how it works. Anytime a rational function gives you 0 in the denominator, you're going to have a vertical asymptote at that value of the variable. I'll drive that point home here in just a second. Couple more things here about these graphs. All right, so we just talked about here a minute ago, I highlighted for you, right, the vertical asymptote. Here's what I like. A vertical asymptote is a vertical line that the graph of the function will approach but never touch. We talked about this, we actually looked at these when we were graphing exponentials and logarithms. With exponentials, we had a horizontal asymptote, and with logarithmic functions, we had a vertical asymptote. And I told you in that chapter, chapter 7, that since we're sort of free-handing these graphs, I'm not going to be super picky if your graph really kind of touches the asymptote. Just please don't cross them, all right? Do not cross the asymptotes. Well, same thing here. Technically, it's a line that it will approach but never touch. Again, we're free-handing these graphs. When we actually start graphing, if you touch the asymptote, I'm not going to freak out. Just do not cross the asymptotes, all right? I'm going to take off a lot of points if you cross the asymptote. So I have a vertical asymptote. A vertical asymptote is a line that the graph will approach, a vertical line the graph will approach but never touch. Now again, my reciprocal function, if there are no transformations, so, sorry, that's a highlighter, I want my pen. If there are no transformations, what that means, if there are no transformations, that means that h is equal to 0. And if h is 0, the y-axis will be the vertical asymptote. Which we'll abbreviate VA. So, if there's no transformations, h is 0. Guess what controls the vertical axis? It's h. If I have some value of h, that's going to shift my vertical asymptote. But if h is 0, then the y-axis, right there, y-axis is my vertical asymptote. Okay, what about horizontal asymptotes? Well, horizontal asymptote is a horizontal line that the graph of the function approaches but never touches. And again, if there are no transformations, then k is equal to 0. Shouldn't surprise you one bit. If h controls the vertical asymptote, k will control the horizontal asymptote, right? If k is 0, then the x-axis is the horizontal asymptote, right? You guys can see that. If this is my horizontal asymptote, as k changes, either shifting the graph up or shifting the graph down, that horizontal asymptote will shift up or down as well. All right, so here you go. Again, I just want to drive this point home before we move on to some problems here on the next page. You cannot divide by 0. Division by 0 is undefined. So what that means is anywhere you have division by 0, it's going to be a vertical asymptote when you graph that rational function. So anywhere you have division by 0, anytime a variable, a value of a variable gives you division by 0, it will show up on the graph as a vertical asymptote. So anywhere you have division by 0 will show up as a vertical asymptote. Let me show you real quick. Here you go. Just a couple of real quick examples. What if I gave you y equals 1 over, let's do x plus 3. Well, this is real easy, right? 1 over x plus 3. Well, what if x is a minus 3? Minus 3, x equals minus 3 will give me division by 0. X cannot be a minus 3 because that gives me division by 0. What that means is on the graph at minus 3, I will have a vertical asymptote. So already, we haven't even taken a look at our first graphing problem yet, and I know right away that at x equals negative 3, I'm going to have a vertical asymptote if I were to graph this function. Why? Because negative 3 gives me division by 0. Division by 0 is undefined, and on a graph, that will manifest itself as a vertical asymptote. That's where it's going to be. Again, I'm just driving this point home. Let me give you another one. What if y is equal to, let's do 1 over x minus 2. Well, if you have 1 over x minus 2, x equals plus 2 would give you division by 0. So what does that mean? Well, that means if you were to graph this function, right, if you were to graph this rational expression, or I'm sorry, graph this rational function at x equals positive 2, because positive 2 gives me division by 0, I will have a vertical asymptote on my graph at x equals 2. Again, one more just to really sort of drive this point home, because we're going to see this a lot here in just a second. Y equals 1 over x. What gives me division by 0? Well, when x is equal to 0. Again, this is our parent function, right? When x is 0, I get division by 0. That means x cannot be 0. When x is 0, it will manifest itself on my graph as a vertical asymptote. Vertical asymptote. Vertical asymptote, right? So guys, the idea is this. Any value of x that gives you division by 0 will show up on the graph as a vertical asymptote, all right? What we're going to do is head on over to the next page of the notes. We'll look more at restricting the domain and finding the intervals on which a domain is actually defined, all right? Head on over to the next page of the notes. I'll show you how those problems work. I'll meet you there.